thank you for having me back. It's really nice to be here. I was here last time to talk about the origins of the universe. So I guess the next step there then is how we understand where the life in the universe came from, specifically us. This quote I've picked to open today because Arthur Eddington, if anyone has heard of him, a few of you might have. I think I mentioned him last time. He is kind of a big name in my field. So I'm a stellar physicist. I look at stars. Arthur Eddington, about 100 years ago, was one of the first people to suggest the mechanism by which stars give off light, nuclear fusion in the core, which we're going to talk a little bit about today. But this quote particularly kind of sums up what we want to talk about today. This idea that really all we are is just kind of bits of long dead stars that have gotten a little bit cold and become self-aware. So if you want to leave now, that's basically where we're going to end up in about an hour. But we're going to also talk about something else as well. So apart from this idea of being forged in stardust, the second half of this title is our place in the universe. This idea of life existing on Earth and whether or not it exists somewhere else. The things that have gone into making us, they exist everywhere. And the chemistry, the physics that have gone into making us, they exist everywhere. So surely there must be somewhere else, right? So what are the probabilities of that? And why haven't we seen anything else? So we'll go into a little bit of that at the end as well, with a physics perspective, obviously. I've already been introduced, but I should probably just let you know I am a stellar physicist in training. I'm submitting my PhD in astroseismology in May. So I look at dancing stars. I look at pulsations in stars. These stars kind of wiggle and jiggle a little bit and they change their light. And I can use that to do seismology on them in the same way that we do seismology on Earth. And that tells us what they look like inside, which is kind of cool. And then people kind of, once I've told them that, they zone out when I start explaining what I actually do, which is sit in a dark room staring at computer code day in, day out for nearing 80 years now. So it's not quite as romantic as it sounds. And I also do teaching as well. So that's me. We're going to start by talking from a physicist's perspective. What is life? Or rather, what are the requirements for life on Earth? If we're going to try and ascertain where it all came from, then it might be worth starting by discussing what we think life actually is, or specifically, what does it need? NASA has got a handy definition, a very romantic way of looking at it. Life is a self-sustained chemical system capable of undergoing Darwinian evolution. It's not really looking at the beauty of the whole thing, is it really? But you can break that into three things. You can look at the three key things there that we want to discuss. Two of them we're going to quickly touch on at the beginning here, and then this idea of chemical systems we're going to focus on a little bit more. The first thing we want to talk about is this idea of self-sustaining. Now, we are all self-sustaining. All life on Earth is self-sustaining. And for that to happen, there needs to be energy. It needs to be an awful lot of energy. It might not seem apparent looking at me, but it takes an awful lot of work for this to happen, right? Where energy flows, then chemistry can become organized. That's the key thing that we want to remember here. Like, in order for chemistry to become organized, and that's what we are organized chemistry at the end of the day, you need to have an awful lot of energy. The graphic on the screen suggests most of that comes from the sun. If there is life out there in the universe, apart from here, it will more than likely be orbiting a star, because the stars are the conduits for this. We don't break the second law of thermodynamics, although we are very organized structures. Entropy is still completely fine. It's just that we use an awful lot of energy and we give off an awful lot of energy. The other thing that we want to look at is this idea of Darwinian evolution. Now, I am not a biologist. I'm not an evolutionary scientist. But the key thing I want to take from this slide is this idea, again, from a physicist's perspective, time. Time is what is needed here. Specifically, this idea of something like us, which is very complex. It can happen if you have enough time. If you inject enough time into the scenario where, for example, you get a planet like Earth, born 4.5 billion years ago, around the sun, and have a environment that is able to stay fairly amenable for that 4.5 billion years, then evolution can lead to quite complex things like us. The other key part of this, obviously, is this idea of being able to store and share, a romantic way of putting that information. And we need to share this imperfectly, right? This idea of evolution requiring not just storing and sharing, but storing and sharing imperfectly. So every time there's successive generations, this survival of the fittest requires that this change to the genetics will somehow lead to some benefit to the subsequent generation, right? And if that happens enough times over a long enough time scale, complexity ultimately is favored. This idea of a complex being like us ultimately getting to this point is favored. The final thing from this romantic description of what life is from NASA is this idea of chemistry. And this is what we're really going to focus on for the next few minutes. Life can arise from diverse molecules, and it needs to be diverse molecules. We're going to look in a second at what chemistry makes all life on Earth, not just us. Obviously, we're focusing quite a lot on us because we are very self-centered and we like to know where we came from. We're the ones sat in this room thinking about this stuff. But all life on Earth requires complex chemistry. It's not just hydrogen and helium. It's carbon, hydrogen, oxygen, nitrogen, phosphorus, neon. Lots and lots and lots of stuff makes life. It has to be flexible as well. It needs something to enable it to be changed over time. We are not just a static bag of chemistry. We are constantly taking new chemistry in, using that, moving it around our bodies, and then spitting it out again. It needs to be flexible, and it needs to have something to assist that flexibility, i.e. water. As I alluded to, we are this collection, this bag of chemicals. This is what makes a human. Has anyone ever seen the acronym CHON before? CHON. It's kind of a physicist's way of looking at what life needs to be. If you look out in the cosmos and want to try and find something that's alive, you would, first of all, want to see if there is carbon, hydrogen, oxygen, and nitrogen there, because most of what makes us is those four things. About 96 to 97% of us and all life on Earth, for that matter, is composed of those four elements. But it's not just those four elements, right? There are lots and lots of other things. We wouldn't be alive if it wasn't, for example, for calcium, potassium, sulfur, sodium, molybdenum, iodine, all those things, although they're there in trace elements, very, very tiny amounts. If it wasn't for those, then we wouldn't be around. However, where did all those things come from? If we need all of those things to exist, what is it that has driven the universe to put all of those things here on Earth? Where did the Tron come from, if you like? The other thing, and we mentioned this briefly, this idea of the chemistry that makes us needs to be mobile. Water is the key solvent in this case. It's very important. If we were searching elsewhere for life, again, we would be hard pressed to find life based upon what we know on our one small sample size of one. Life on Earth needs water. So if we're looking elsewhere, we're looking for water. It's valuable because it's a polar molecule, which means it can transport ions specifically. It's very, very good at that. There are alternatives, things like ammonia, for example, and there are other potential chemical combinations that could do similar things to what carbon, hydrogen, oxygen, and nitrogen do, along with water. But we don't see those on Earth, right? We don't know what they are. So if we were looking elsewhere, we'd be looking for water, and we'd be looking for carbon, hydrogen, oxygen, and nitrogen to begin with. So where did it come from? If we are made of these things, and life on Earth requires these things, where did it all come from? Well, the Big Bang is obviously a good place to start. This idea of all chemistry starting in the Big Bang, but there was only two things made in the Big Bang. Pardon me. Helium in small amounts, hydrogen in large amounts. The Big Bang happened about 13.8 billion years ago, and in that instant, all the nucleons, the things that make atoms were all made. All of the atomic components that then went on to make everything else were made, but there was nothing more than hydrogen and helium. For everything else, phosphorus, nitrogen, everything else, something else needs to happen. The reason why this happened was because in the Big Bang, it was very, very hot in the first few moments, and then because it expanded very rapidly, it became more diffuse. The temperature dropped very, very quickly to the extent that no nuclear fusion could take place, apart from creating 25% of the universe being helium. So all we had in the Big Bang was hydrogen and helium. So where did everything else come from? Stars, specifically the lives and deaths of stars. We are, and he wasn't over egging the custard here, we are literally star stuff. If it wasn't for the stars, we wouldn't be around. So I'm going to talk a little bit about how stars have led to the chemistry that we need. So they are, as the slide says, cosmic chemical factories. What they do for the vast majority of their lives is fuse hydrogen in their core, in the first instance, into yet more helium, which is not particularly useful for us because we need other things as well. In fact, our lives, our bodies don't have much helium in them at all, like negligible amounts. But what they do, depending on how big they are and how they are going to end their lives, is create lots of other elements for us to then use and for the universe to then recycle into subsequent generations of stars. So how a star progresses through its death cycle specifically is of interest to us. We're going to look at the sun first because the sun is our nearest star, and it's quite interesting because it's our lovely local bland mundane star, and that is good for us because if it wasn't bland and mundane, we wouldn't exist. And then we'll talk a little bit about giant stars as well, because those are the ones that really give us some quite interesting stuff. The sun, along with more stars out in the universe, is what is called a main sequence star. A main sequence star is another fancy term that just means a star in the middle of its life. Stars, their main job for 90% of their life is to do this one thing. They fuse hydrogen in their cores into helium, nuclear fusion. They squash protons together at 15 million degrees, and every now and then one of those protons will just randomly turn into a neutron because of another lecture that I could give, but I'm not going to. And then when that happens, eventually you get helium. If that happens enough, the core of the star will eventually become full of helium, and all of the hydrogen in the core will have fused. Interestingly enough, this reaction, and I mentioned there that the nucleons, the protons, will turn into neutrons. That doesn't happen very often. There's just lots of stuff in the sun, an awful lot of stuff. Enough stuff that even though these strange subatomic reactions take place, that it doesn't burn itself out very rapidly. If it did, then there would be no sun, there would be no stars. We're very fortunate that this nuclear reaction, this subatomic reaction that takes place to turn these protons into neutrons and then create helium and therefore have nuclear fusion, is a kind of very ordered and structured reaction. Not too many numbers in this talk today, but I thought this was an interesting one. 660 billion kilograms of hydrogen turn into 656 billion kilograms of helium. Now there's a deficit there, right? There's 4 billion kilograms of mass disappearing. Anyone know where that's going? I mean, I think it's on the slide, isn't it? But like, it's Einstein's theory of E equals mc squared, right? Energy and mass equivalence. Nuclear fusion is an excellent and very good way, efficient way of giving off energy. The mass that is lost is given off as gamma rays from the core of the star. This mass difference, by the way, about 4 billion kilograms being lost, that's the equivalent of about 15 Wembley Stadiums worth of material every second. The sun is turning that into energy every second. It's been doing it for about 4.5 billion years. It will continue to do it for about another 4.5 billion years. Once it has used all the hydrogen in its core, and I want to emphasize it's just the hydrogen in the core. All the hydrogen outside the core stays put. When stars die, they are still mostly hydrogen. They don't burn through everything. It's just the stuff in the core. What will be left is helium ash, which means nuclear fusion will stop very briefly because it's no longer hot enough. When nuclear fusion stops, the outward pressure from the core of the star, those photons, the light, that energy that is being given off, stops for a second, which means the outer layers are not getting pushed up anymore. it's not in equilibrium, and suddenly those very heavy outer layers drop down. They squash the center of the star. And what happens is called a helium flash. And the helium, with all that pressure, will suddenly rise well beyond the 15 million degrees Kelvin that is required to fuse hydrogen and get to the requisite temperatures of about 100 million Kelvin needed to fuse helium. And at that point, the sun will turn into a red giant star, and it will start fusing helium in its core, and it will start fusing helium into carbon. So this is the first point at which we start to get something other than hydrogen and helium in the universe, when stars transition away from this main sequence and start burning, or rather fusing, helium into carbon. And we get this sort of onion structure, this idea of a core where the fusion's taking place, and then there's an ash forming around it, and then around that is the outer layers of the star. Other stars, as we'll see in a second, get quite a lot of layers forming as different chemicals start fusing in the core as the star gets incrementally hotter. Not so for the sun. The sun being kind of a very middle of the road star, and again, I emphasize, I'm not being disparaging. We like the sun being a middle of the road star. Once it has finished fusing all the helium, that's it. The ash that remains in the middle there will be carbon with a tiny, tiny bit of oxygen, but mostly carbon. Even when it stops fusing and that pressure then drops down and squashes it, it will not be able to reach the requisite temperatures to fuse carbon into anything. At that point, it will stop. The sun will die. And instead of fusing anything else, those outer layers that have dropped down will bounce off that core and dissipate out into the cosmos. This is the Helix Nebula. This is the kind of death throes, the end of the line for a star of equivalent size to the sun. This is what the sun will ultimately look like in about 6 billion years or so. In the middle, a tiny, tiny little white thing is what's left over. The ember, the core, which is called a white dwarf. It is just a sphere of carbon, and that's all that will be left over when the sun dies. It's quite beautiful. It's nice to think that when the sun dies, it will form something like this, something astoundingly beautiful. These kind of rings, these structures that you see, we think are to do with magnetic fields in the stars. So depending on how the magnetic fields in the stars are structured, the nebula that is formed after it dies will look slightly different. But if you Google any kind of planetary nebulae, they all look incredibly beautiful. They're always quite symmetrical, and they always look incredible. So if we've got stars like the sun, which don't fuse anything more than carbon, that means we're still missing over 100 elements from the periodic table. So where do they come from then? So I've used this image here. This is a familiar constellation this time of year on its side. This is Orion. There's two stars here of interest to us, at the bottom there and up here as well. Two massive stars. What we mean by massive stars is they have a lot more stuff in them than the sun does. They weigh, or rather they have, about 15 to 20 times more mass than the sun. They are big, big stars. Betelgeuse and Rigel. Betelgeuse is a red giant star nearing the end of its life. Interesting for us because it's currently going through some of the stuff we're describing. Rigel will be going through that in a few million years' time. These stars, because they're so massive, they've got so much material, they are burning through the material much, much faster. Whereas a star like the sun, a small star, will burn through its material over 12 to 13 billion years. It will have a lifespan of about 12 to 13 billion years. We're about halfway through, so we're fine. Stars like Rigel and Betelgeuse will only live for a max of about 10 to 15 million years. Not billion, million years. So like 10 to the 3 away, right? It's like a whole level lower. So these stars, especially Betelgeuse, the fact that it's a red giant now means that we can fairly accurately guess it will probably die in a few thousand years, not in a few million years. It's probably quite close to going. Rigel, once it turns into a red giant, again, we'll see in a second, they don't stay as red giants for very long because they are massive and they burn through things so, so quickly. So for a star about 25 times the mass of the sun, a bit bigger than Betelgeuse and Rigel, they will be on the main sequence for about 7 million years. Not very long, really. But once they've done that, the subsequent eras of the star's life are very, very short. So once it's fused all the helium, it will have carbon in its core, same as the sun. But because it's massive enough, it can then keep fusing heavier elements. It can go through carbon, neon, some oxygen, silicon, and quite a lot of other things around that as well in smaller amounts. It's not just those 5 or 6 on there. It will go through about 50 different elements. The interesting thing about this slide, obviously, is the timescales. The main sequence only lasts for about 7 million years, fair enough. But once we get to these areas down here, neon fusion should only last about a year. Oxygen fusion, silicon fusion, a day. Once silicon has fused, what happens there is we get left with iron. And when you get iron in the core, stars don't like that. Stars don't live through that. Having iron in the core of the star is the end for that star. The reason for that is to do with nuclear physics. Fusion can't take place beyond iron, at least not in the star, because of what we call the nuclear binding energy. Sorry for the graph. There are 2 kinds of elements. Ones that give off energy via nuclear fusion, i.e. in the core of a star, where they're fusing elements together, energy is given out. Other elements give off energy by radioactive decay, fission. Those are the kind of reactors that we have here on Earth, right? Fission reactors where a radioactive isotope will decay, and when it decays, part of it will break off, it'll form something different, and it will give off radiation. Iron sits right in the sweet spot, in the middle. Fusion can no longer take place in a star with iron, because in order to create things more massive in terms of chemicals, in terms of elements than iron, more energy needs to be put in than the fusion would give out. So nothing can happen anymore. When you get fusion finished in the star and you get iron in the star, these red giants will then stop. But we are still only halfway through our periodic table, right? We are still only up to iron in the periodic table. We know there's another 50 or so elements above iron with increasingly large cores, nucleons, with lots and lots more protons. Where do they come from then? Where does the energy come from to fuse, bind these cores of atoms together to make these bigger and bigger atoms? Atoms that I should say are in us as well, right? Well, it's because of this chap that we have a theory about this, Sir Fred Hoyle. Now, Fred Hoyle is, I should say, he's a local lad. So he's from West Yorkshire, my neck of the woods, from around Keighley Way. And there's a great video if you are interested in hearing him talk about his work. Richard Feynman, the great physicist, was a good friend of Fred Hoyle. And there's a video from the 60s or 70s of them walking in the countryside over in West Yorkshire, just talking about physics and enjoying each other's company. It's very pleasant. But Fred Hoyle's more famous now, actually, because he was a bit of a grump. He was not a particularly amiable chap. And when he was working in the 40s, 50s, and 60s, his main area, similar to me, was stellar physics. But he looked a little bit at kind of the origins of the universe, as a lot of people did then. And at that time, the birth of the universe was a big topic. And his naming of a particular thing is what he is famous for now. But he named it in a disparaging way. Anyone know what it was? Big Bang. Yeah, so the Big Bang, we call it the Big Bang because of Fred Hoyle, but he didn't give it that name because he was impressed with the theory. He thought it was absolute bunk. He didn't like the idea of a Big Bang theory. He liked the idea of a steady state universe, this idea of a universe that's just been around forever and there's no kind of big, vast, interesting beginning in the way that we now have pretty good evidence to suggest happened. So he said, what was it? Some sort of Big Bang? And that just stuck. I don't think he said it like that, but it was within that kind of vibe. His other main contribution, and the thing that we're interested in, was a paper where he suggested a mechanism by which massive stars might be able to create these heavier elements, because up until the 40s and 50s, we didn't know where they came from, right? We knew that by modeling and by observation and some vague lab work that we were able to do, we could create these elements up to iron, but we didn't know where they were coming from. He was the first person to suggest this mechanism by which heavier elements could be made. and it was supernova. When these massive stars get iron in their core, this iron ash will obviously stop fusion. And the same thing will happen as happens in the sun, right? The outer layers will suddenly come crashing down. However, when they come crashing down in a massive star, because this star is so much more massive than a star like the sun, it is not going to be quite a calm and pretty shrugging off of its outer layers to create a planetary nebula. What it's going to be is a massive, first of all, implosion, and then, depending on how massive the star is, two things could happen. Either this huge implosion will create so much pressure that the core of the star will become hyperdense, and all the iron ash will suddenly turn into neutrons, and it will become a neutron star. And we see these. If you've ever heard of pulsars, pulsars are neutron stars, rapidly spinning neutron stars. The other thing that can happen if the star is sufficiently massive, even bigger, is that the material becomes so dense that it creates a black hole, and no light or matter can escape it. It becomes so dense, and the material then dissipates out from whatever is left over, either the neutron star or the black hole, and it forms another kind of nebulae, supernova remnant. This is Cassiopeia A. This is a beautiful image. Again, what we're seeing here is the remnants of a dead star. What we're seeing in the middle here, instead of a neutron star as we did with the Helix Nebula, this is a neutron star in the middle. This is a composite image from three different space telescopes, Spitzer, Hubble, and Chandra. And each of those three space telescopes are looking in different wavelengths. The different components of this ejector from this supernova are at different temperatures, and they're emitting light in different wavelengths. So we use different telescopes with different optics, different capacities to see these different parts. And what we're seeing here is different chemicals emitting at different wavelengths. These supernova remnants, or rather the moments of the supernova, these split seconds, these minutes really, or few seconds after this implosion takes place and then this ejector takes place, they have enough energy to start having neutrons rapidly come together. This process is called the rapid process, the rapid neutron capture process, whereby atoms heavier than iron can come together and start to form. So a lot of the stuff that we are made of, that life is made of, that the stuff that makes Earth is made of, is formed in these gargantuan explosions from the deaths of massive stars. So the periodic table, again, this is from NASA, this is a periodic table based upon where the stuff that we are aware of comes from. There's a few of them on there, like these ones at the bottom, man-made ones. There's a few of them up here, so obviously like stars like the sun. There's a couple of them supernovas, and there's a couple of other different things on here which I'm going to get to as well. It's not just supernovas that create these things, but a lot of it is. So if we look at our map of what makes Earth this kind of graphic, oxygen, most of it comes from supernovas. Some of it comes from inside stars as they're fusing, but most of it comes from supernovas. So the oxygen that we rely on, all from supernovas, or mostly from supernovas. Carbon, we know where carbon comes from, dying low mass stars. Phosphorus, potassium, sodium, supernovae, magnesium, all supernovae. So all of these things that we take for granted as existing, all of it is recycled material from the deaths of these stars. There's one special one on here, just one, with an asterisk at the bottom. Iodine. Iodine and a few other things, like, for example, gold, we haven't seen their signatures in supernova remnants. We don't think that even supernovas have quite the energy budget to even create things like iodine or gold and a few other things as well. And for many years, scientists were racking their brains trying to fathom what could possibly have a high enough amount of energy, what could exist out there in the cosmos that would create enough oomph to give energy to fuse some of these other things that we're not seeing from supernovae. And it's only recently that we've started to see these things. The theory was, and it was proven, theory was that it was two objects colliding in space, these remnants of supernovas, neutron stars. So they're already made of neutrons, and neutrons are quite important for nuclear fusion. Obviously, these occurrences must be very, very rare, right? But enough of them must happen that it creates some of this stuff. And it was only a few years ago that we saw them for the first time. And this is a really interesting observation. What you're seeing here is a flash viewed by the Hubble Space Telescope. But this was one of the first multi-messenger observations of something. What I mean by that is we observed it in light, and we also observed it using the warping of space-time caused by the collision of these two neutron stars. The mathematical theory predicted that gravitational waves should propagate from something like this. Me doing this causes gravitational waves to propagate, but they're so small that we would never be able to measure them. In order to measure gravitational waves, we need something massive happening. Neutron star collisions were theorized to be one of those things. And it was neutron star collisions that we first measured using gravitational waves a few years ago. The signal from this collision matched exactly what the theory suggested it would be. And interestingly, we actually received the gravitational wave signal using LIGO, the interferometer, a little bit before the visible signal from Hubble. So the LIGO interferometer received the signal, triangulated where the signal should come from, and then moments later, a little bit later, Hubble was able to see it. The reason why there was a delay is because the light from this collision had to pass through interstellar space, and interstellar space, although it is mostly a vacuum, mostly empty, there is gas, there is dust, there is intervening stuff that kind of inhibits the path of this light and slows its path down very slightly. The light doesn't dip below the speed of light, but it pings around in clouds of gas a little bit. So the light arrived slightly after the gravitational signal, which is again what we would predict, which is amazing. It's quite incredible that we're able to do that. Theory predicted it happens, and we saw it happen for the first time. So iodine and plenty of other things as well, born in these circumstances. Who's wearing a wedding ring, a gold wedding ring? I'm sure a few of you will be. That gold was born in a neutron star collision. Isn't that mad to think about? Like, how insane is that to think? Like, all the stuff that we're seeing in this room, like iron, everything that we are made of, all the stuff that we just see, like all the materials is just there for us and we take it for granted, but it doesn't just appear, right? It was made in these circumstances, and it just boggles my mind that all this stuff has happened for billions of years before the sun was even born, right? The sun was born 4.5 billion years ago, so the universe had about 8 or 9 billion years to cycle through successive generations of stars before it got to the sun. These massive stars, as we know, only live for a few million years. So over the course of 8 or 9 billion years, many, many, many massive stars will have born and died. These supernovas will have happened again and again and again. And there'll have been enough neutron stars that even though these collisions don't happen very often, there's enough of them that those materials then are created and propagated out into space and form the next generation of stars. And our sun was lucky enough to be born from a cloud of random detritus that had some stuff in it from a neutron star. And that's why we've got all this gold and stuff, which is mad. So how did that become us then? If we have got all this bad stuff that's come from these supernova, from neutron star collisions, from the deaths of stars like our own, and from other strange things like high energy collisions of stellar like gamma rays and things like that, we think caused the creation of some particles out there, not so many, but some. How did that become us? It's all well and good me saying, okay, we've had successive generations of stars that have died in these interesting and fun ways. Some of them have collided and made this stuff, but what was the next step? Well, as I've said, we have had several generations of these stars born and die, and they have fed into us in a meaningful way. We are very much the next generation, and when we die, when our star dies, that will feed into another generation as well. How this happens is when these stars die, these massive stars in particular, they haven't traveled very far from when they were born, where they were born. This is a picture of a beautiful galaxy, a spiral galaxy, much like our own galaxy, the Milky Way. The Whirlpool galaxy as well is a beautiful example. We can see some very distinct structure in this galaxy. We can see some dark patches. These are dust patches, and around those dark dust patches are two things. There are very bright blue areas, and there are some quite distinct red areas as well. Those red areas are supernova remnants, and the dark patches are clouds of dust. Spiral galaxies, like the one that we live in, are spiral shaped because the stars, massive stars specifically, don't have a chance to escape from the area where they were born. They only live for a few million years, and it takes much, much longer to orbit a galaxy. The sun has been orbiting for many, many times around the Milky Way galaxy. It takes about 240 million years. With that in mind, a star that's only going to be around for 10 million years won't travel very far around the galaxy. In fact, most massive stars are born and die very close in proximity. And a lot of these red giant stars, therefore, never leave the spiral arm where they were born. And in fact, spiral arms are technically signs of giant star birth and death. That's why we see them, because the stars that we see, all the stars that we can see in this image are massive stars. The gaps in between the spiral arms, they're full of stars as well. Stars like our sun, they're just from a distance, not bright enough to see. The spiral arms are visible because of the massive stars. And the deaths of the massive stars are there to see because of the supernova remnants and the clouds of dust. And what happens in those areas is when these stars die, the material over time, I don't want to emphasize it takes time. It's not a short period of time. It's not a few weeks or months. It is millions of years. It can start to coalesce, right? We've got nothing if not time. We've had a universe around for billions of years. The Milky Way's been around for about 10 or 11 billion years. This material will eventually coalesce in these spiral arms. We'll get these beautiful different kinds of nebulae. These are dusty nebulae. There's not a lot of this stuff out there, this heavy material that is born from these deaths of stars, this heavy elemental stuff which forms this dust, but because it is there, it blocks light, so we see it. There's not a lot of it compared to all the hydrogen in the universe. We just don't see the hydrogen in this picture. What happens is, over time, these things come together and they form incrementally smaller nebulae. In the middle of this nebula is a young giant star that has just formed, and we have these areas of star birth, these stellar nurseries. This is the pillars of creation, one of the most beautiful images that Hubble's ever taken. Quite a poetic name for a scientist to come up with as well, the pillars of creation. It's an area where there are many, many infant stars being born. This is a Hubble image. I haven't got the equivalent image, but the Webb telescope, which observes in infrared, can see through the clouds of dust and can see many infant stars, these protostars, these young stars forming. So if you're ever interested in looking for that, Google Webb telescope, pillars of creation, you can see through. What happens once these cores of dense material start to coalesce is there will be an over-dense region. There'll be a region where there's just a little bit more stuff, just a little bit more material than in one of the other areas. And that means it has just a little bit more mass and gravity can start to take over. And when that happens, it's kind of a chain reaction. Free fall starts to happen and the material will gradually speed up and it will come together and form a core of this material. And when that happens, it speeds up. It will have a net rotation. If you've got 100 billion particles, 100 trillion particles in the cloud, and half of them plus one are walking in this direction and half of them minus one are going in this direction, that is a net rotation. And eventually that net rotation will dominate and it will spin. And when it spins, it collapses faster, and the conservation of angular momentum tells us that. As a cloud gets smaller, it will spin faster and faster and faster. A nice example is obviously when you see a very skilled dancer on ice, when they have their arms out, it's very slower, and if they bring their arms in, physics does this nice thing, and it tells them to spin faster. The same thing happens with these clouds of dust and gas out there in the cosmos. As they get smaller and smaller, they spin faster and faster, throwing more material on the core of these things. And eventually what happens is there is enough material in the core of these collapsing clouds that we get a star forming. A protostar to begin with, but as more and more material falls on it, it gets denser and hotter, and eventually a star forms. We're not interested in this case in the star. What we are interested in is all the stuff around it. These clouds, as they get smaller and smaller and smaller and spin faster, another law of physics says that as things spin faster and faster and faster, they like to flatten out and form disks. And it's those disks where all the fun stuff happens, where the planets are formed. All this extra stuff that is being formed by all these other stars, this is where it comes into play. It's an afterthought almost from the birth of the star. The material that is there will start to coalesce and it will sediment into the middle of the disk and it will come together. And depending on how far away from the star it is, there'll be different temperature gradients, right? The closer to the star you are, the hotter it will be. So there'll be less volatile materials like waters, like ices. Further out from the star, it'll be cooler. and there'll be more ices and more kind of things that allow rocks to coagulate. Ice likes to stick together, rocks less so. That's why we have big planets and small planets in our solar system. That's why we see big planets and small planets out there in other solar systems. Closer to the star, the photon pressure from the star is sufficient to push away these lighter gases, the still gaseous water, which there will be, and it'll push it further away to beyond what we call the snow line. And beyond the snow line, it is cool enough for water to become water ice. And when that happens, that will stick together quite quickly, and it will stick to the rocks out there. And the formation of things will happen much, much quicker. So there's a very, very clear divide. And we see it out in our observations of these infant star systems as well. And we see it in our own solar system. Interior to this snow line, things will stick together, but slower. And they rely on electrostatic forces, sticking together from small things very gradually until they form bigger things that will eventually have enough gravitational mass to form planets and planetoids, things like that. Out there beyond this snow line, because there's ice, this happens much, much quicker, and the planets can form much, much faster. And you get giant planets like Jupiter, like Saturn. The reason that's important is because then when the sun or the star is sufficiently evolved enough, its photon pressure, the amount of light it gives off, will then push away most of the remaining light material, and planetary formation will stop. We think that happens in a very strict order in our solar system, and now we're observing it out there in other systems as well. So this is a artist's impression of what we think it looks like, and this is a direct image from the European Southern Observatory in Chile of an infant T Tauri star system. And what we see here is exactly what I've described. So in the middle, we've got this infant star, and we've got this protoplanetary disk around it. This protoplanetary disk, can you see the gaps? That is where the planets are forming. So we can see this disk, which hasn't been pushed away yet because the star is still quite young and it doesn't have enough photon pressure to push the material. And these gaps tell us that there are planets forming around this star, which is kind of cool. The only thing, I guess, that's interesting in a weird way is that we are just kind of the afterthought of stars, right? We are I've used this word once already, but we are detritus. We are stuff that just happens to exist because of stars. We now think, when we look out there, most star systems have planets around them. Planets are just a natural occurrence in the grand scheme of stars being born. Planets just seem to exist because of this. As these clouds shrink down, stars form, and as the clouds flatten out, planets form. We just think this is how it happens. And that's why we get a solar system. Now, interestingly, again, all this material coalesces and forms these planets, and all this stuff that I've described then comes together on these different planets. There's nothing particularly special about Earth, apart from obviously us being on it. A lot of the stuff that I've described, all these heavy elements, we find them everywhere in the solar system. Water is everywhere, as we'll see in a second. So with that in mind then, what does Earth offer that life specifically needs that's different to elsewhere? Or is it different to elsewhere? Where did life come from in that case, right? What was it that made this puddle, if you like, a few billion years ago, 4 billion years ago, of chemistry turn into life? We don't know. There is an experiment, which I'll get to in a second, that kind of suggests at least a mechanism for it starting to happen. But as of yet, there has been no experiment that has been able to get a puddle of inert materials and create life from it. I'll put this quote up here. I never knew this until I was putting these slides together. I was looking for quotes from Darwin about evolution, and I stumbled upon this one where he actually predicted quite accurately, nearly 150 years ago, the mechanism by which we now think that the early ponds of material in the early Earth might have had action upon them to create life. It's quite an interesting thing that Darwin was able to kind of prognosticate this all that time ago. This idea of a warm little pond. And I think that's mainly what the main theory is, a warm little pond where there is some chemicals and an energy gradient. That's the key thing. The sun would be important at this point, and electricity from lightning and things. There was an experiment called the Urey-Miller, or the Miller-Urey experiment, from about 70 years ago in the early 50s. And they recreated these early environments in the beginning of the solar system. in the beginning of the Earth, when we think the Earth was still quite a volatile environment. They put together just a few things in this experiment: ammonia, methane, water, hydrogen. And just after a few days, with a few sparks, some of these very basic ingredients, which we see out there everywhere in the cosmos, methane and ammonia are there, they started to come together. They weren't forming life. I want to emphasize that. They were not forming life, but they were forming the constituent parts that could then go on and form life. What that next step is, I invite you to hazard a guess, but I'm not an evolutionary biologist, and I do not know. There are many theories, but there's been many, many equivalent experiments that have developed and added to this over the last few decades. But simple gases, simple chemistry, and a few key ingredients that are universally available came together. There's nothing special about the things that they put in this experiment. Nothing special about the Petri dish at the start of the Earth's journey into life. Nothing. It's everywhere. And in fact, even the water that we think makes us special, this water that I emphasize as being super, super important at the beginning of this talk, it's everywhere in the solar system. Everywhere. In fact, we don't even have the most of it. Like some of the moons of Jupiter and Saturn have more water than we do. Europa and Enceladus, which we're going to get to in a second, Pluto has got more water than us. So water, again, not special to Earth. We have got lots of it, and it is very, very useful for us, but it is not unique to Earth. It's everywhere. We see it in clouds of nebulae out there. We can see its exact signature when we do radio astronomy of some of these telescopes. Using our very simple radio telescopes on the University of York campus, we can point them to the core of the galaxy and see some clouds of material and see water in the core of our galaxy. It's just there. It's a universal thing. Mars used to have water. There's evidence of water on Mars. Where it's gone, we're not quite sure. Either the lack of atmosphere or the death of the atmosphere, I should say, means that it would have evaporated into space because Mars lost its atmosphere. But recent observations from seismographs that we've put on Mars, there's a little fleet of robots. Mars is the only planet in the solar system in the entire universe that we think actually that is populated entirely by robots. One of them is doing seismology on Mars. And a few years ago, 2 or 3 years ago, it sensed a small quake, and the quake had the signature that suggested that actually there's quite a lot of water a few kilometers below the surface of Mars. So Mars might still have some water. So water is everywhere, but that chemistry that we see, that we need to exist, not just the like inherent basics, not just the elements, not just the atoms, but the complex chemistry. We find a lot of these out there in the cosmos, in these cosmic clouds of gas. They just exist there. On Mars, these little robots, these rovers have found long-chain fatty acids on Mars. Again, emphasizing this is not life, but it's the stuff that life needs to get going. If that is there in our backyard, it's in comets as well. This is, let me say this right, Churyumov-Gerasimenko, the comet that was in the news about 6 or 7 years ago. We sent a little lander there called Philae. Philae landed on Churyumov-Gerasimenko. And again, it found organic compounds. Organic compounds does not mean the thing is alive, but it means these compounds are the stuff that if you throw them in this Petri dish, eventually those are stuff that would go on and help life to start forming. So we are not unique in that respect in our solar system. So if all of that stuff, all those chemicals, all that water exists in the solar system, then is there life out there as well? Well, this is Enceladus. This is one of the moons of Saturn. My well just there might lead you to think we found life there. We haven't. What we have found, though, is something promising in terms of let's go and search. These that you can see from the surface of Enceladus, this is a photograph that was taken by Cassini. Cassini was orbiting Saturn for about 10, 15 years earlier on this century, and it spotted these geysers, emanating from the cracks in the crust of Enceladus. Enceladus is a water moon. It's got a liquid ocean surrounding a very small rocky core, and on the surface, because it's so cold up there, instead of a rocky crust, it's got an icy crust. And the crust cracks every now and then because of the gravitational forces of Saturn, which makes it crack, and the water will spurt out. They sent Cassini through some of these jets to, and I quote, sniff the material. And when it sniffed the material, it found, again, some of these complex molecules. Again, it hasn't found life yet, but it's found indications that there are materials there that could go on and form life. And there's also things like molecular hydrogen there, which exists in a lot of places deep down in the oceans on Earth where life exists. It doesn't mean there is life, but molecular hydrogen there means it's worth going to take a look. So we haven't found life, and we're not sure that life exists elsewhere in the universe. But if all of this stuff exists in our own backyard, then why have we not seen anything else? And more to the point, what makes Earth so special? If we've got all this stuff out there on Enceladus and Mars had water a few million, billion years ago, then why is Earth special? Well, there's a few specific things that makes life on Earth a prospect that is kind of not unique, perhaps, but fairly special, fairly different to everywhere else that I've described in the solar system. It's all well and good having water on Pluto. It's all well and good having these chemicals on comets, but they don't have this unique combination of things that Earth has, right? It's got liquid water all the time. It's got a moon, and the moon, I can't overemphasize enough, is a great stabilizer for Earth. And the way that the moon was formed is quite a unique and different way that we think a lot of moons may have formed around other planets. So the moon stabilizes the planet and keeps climate broadly okay for us. There may be the odd ice age every now and then, but temperatures don't dip or get too hot in any meaningful way to eradicate life entirely. The moon helps with that. We've got an active geology, which recycles material and puts methane and other things in the atmosphere that really help life. And our atmosphere is still there, and it's not too thick to cause a runaway greenhouse effect. All these things coming together make Earth quite special. But again, this could happen anywhere, right? Not just Earth. So that leads us to the final question of today. We've got another few slides to kind of go a little bit wavy, veer a little bit away from science. So do forgive me a little bit if we get a little bit strange. But we want to ask these questions in an empirical, objective way, right? We're not just going to start talking about ET, but if we've got a universe, and this, by the way, is data. This is real data. This video is from something called the Sloan Digital Sky Survey. It is a projection, a map based upon observations of the positions of galaxies. All of these points of light, not stars, galaxies. Yeah, so this is our local universe. Millions upon millions of galaxies, right? Each of them with as many, if not more, stars than the Milky Way. The Milky Way has got 100 billion to 400 billion stars. We're not quite sure, anywhere in that range, between 100 billion to 400 billion stars, depending on how you ask. These galaxies, every single one of them will have a similar number of stars, right? And in the universe, there are billions of galaxies. So just the simple maths suggests if every star is probably making planets, and there are billions and billions of stars in our Milky Way, and billions of galaxies in the universe, surely, somewhere, it must have happened. Surely. So how can we quantify this? How can we see this? Why haven't we seen them? Where are they? If they are there, if the maths seems so insanely in favor of life existing, and just think about it this way, right? Life happened on Earth like fairly casually. These things came together and Earth just so happened to be fairly amiable towards it. It wasn't long after Earth was formed that life came to be, right? The earliest life on Earth was about a few 100 million, 500, 600 million years, I think, into Earth existing. It happened fairly quickly because life was able to do so. It seems that life might take hold if it can. It seems like a logical progression that stars form these materials, they go into creating planets, and if a planet like Earth has the right materials, then it doesn't seem such a hop, skip, and a jump for it to happen. So that leads us to this question, where is everybody? Which is kind of a simplification of this question from Enrico Fermi, who worked on the Manhattan Project. His question, rightly, was, if we've got all of these stars, and we're only talking about the Milky Way right now, if we've got all of these stars in the Milky Way, and billions of potentially habitable planets and billions of life, potential for life to form, we don't see them. So what is the solution to this? Solution number one is that we are completely alone and actually there is no life and that we are just incredibly fortunate. I don't like that because it just doesn't seem probable, right? It just doesn't seem likely. Perhaps there is billions and billions of planets out there with life that just doesn't reach the level that we have yet, in which case life might be everywhere. But I don't like the idea of this. It might be true, but it seems more likely that other things might be true. That leads us to this question by Drake, Frank Drake, in the 60s. This is called the Drake equation. Has anyone seen this before? Yeah, a few nods. This is an attempt to quantify this in a very haphazard, back of the envelope kind of way. I'm sorry, again, equation time, but the components of this equation basically are individual parameters that can give us an estimation, if we put them together, of how many intelligent planets there might be out there. And bear in mind, these individual parameters, the estimates can vary based upon who you ask. So the first one is the average rate of star formation in our galaxy. We think roughly, and these are back of the envelope estimates, roughly 7 stars born every year in our galaxy. The fraction of those stars that then form planets. Now, this is an underestimate, we think now, because we think most stars form planets. But if we underestimate this and say half of them form planets, that's still a fairly good guess, right? From those, how many of them are in this so-called habitable zone that Earth is in, where it's close enough to its star to have liquid water, but not too close that it's too hot? If 2 stars in every solar system have those, because Mars is roughly in the solar system's habitable zone as well, then that's not a bad estimate. How many of those then actually develop life? I think this might be an overestimate, 13%, perhaps 0.13. Who knows? How many then go on to form intelligent life? Now, arguably, you could say Earth doesn't have intelligent life, but how many of those? Maybe 1%, maybe 1% of those, right? If 1% of those planets have intelligent life, or 1% of those planets with life then form intelligent life, the numbers are getting increasingly small. But even so, how many of those then go on to become intelligent enough to declare their existence, to say to the cosmos, hello, I'm here, come and visit? 10% of those perhaps. And then based upon that, how long does a civilization live? Does it live long enough to do that, to declare itself? Humans have had an approximate life of communicating in meaningful ways for 10,000 years. We've only really been broadcasting ourselves to the universe for about 120, 130 years. But again, putting these numbers in, and do bear in mind, you can massively change these estimates based upon what numbers you put in. About 23 advanced civilizations could exist in the Milky Way. And I want to emphasize, this is just a back of the envelope calculation, right? If we go back, and if you're interested, these slides can be shared with you after this. There's a calculator at the bottom where you can click the link and put your own numbers in and see what numbers you get out. Some of them, if you put some numbers in that seem more realistic, it gets down to 1 or 2. If you put some wild numbers out, obviously you can get millions of different civilizations. If you put a realistic number in, then perhaps 1 might be about right, and that would be us. But if each galaxy then has that 1, that means all those other billion galaxies might have 1 as well, right? So if we move on from this, and we talk about if there are other civilizations out there, and there may be, then why haven't we heard them? This Fermi paradox. Well, to start off with, they probably don't know we're here, right? We have only been broadcasting ourselves out there for about 100 years or so, which means that we have a bubble, a radio bubble of about 200 light years in diameter, right? Radio waves travel at the speed of light, so it's traveled out. Given the size of our galaxy, which is 100,000 light years across, it's a very, very tiny portion of our Milky Way, just a few thousand stars. Even then, I'm sorry to make us sad here, the laws of physics, actually the laws of geometry actually tell us most of those stars won't ever even hear whatever wonderful stuff we've been putting out there. We've been broadcasting wonderful symphonies. We've been sending out awesome plays, Shakespeare. Love Island is out there. And they will never see it because these signals that we're sending out there isotropically in a sphere, the inverse square law tells us that with increasing radius, the surface area of that sphere gets bigger. What that means is that signal that we're sending out is getting thinner and thinner and thinner every passing light year. To the extent that actually just a few dozen light years from Earth is indistinguishable from the background noise of the universe. So they will never hear Dua Lipa. They will never hear amazing things that we're creating. So what does that mean? We can communicate. It just means we need to beam. And that means we have to be thoughtful about where we send our signals. Or inversely, if aliens exist, they would have to be thoughtful about where they send their signals as well. If you send laser signals, that issue with geometry becomes less meaningful, and you can send signals to stars, or rather where you think the stars will be when the signal gets there in a few thousand years, right? So you have to be careful with that as well. There is one example of a signal that was captured by, I think it was the Arecibo telescope, called the WOW signal. It's a great name for a band, WOW signal. It was a one-off about 50 years ago, and it never repeated, from Deneb. I think it was a star. I think it was Deneb. Correct me if I'm wrong. And it never repeated, and no one knows what it was, and it's never come back. No one knows what it was. It wasn't indicating anything. There was no kind of. They weren't playing pop music. They weren't sending any meaningful scientific information. There were no prime numbers or anything as part of it. It was just a weird thing that just blipped, and they don't know where it came from. But if we wanted to do that, if we wanted to broadcast ourselves, not sure we would, then that would be the way to do it. Thing is, though, these civilizations, if they're out there, probably don't know we exist either, right? So why would they? And they're just sending signals willy-nilly to every star to see if they respond. But then, if they're thousands of light years away, it's going to take a long time for us to reply, which is also kind of a problem that we're going to get to in a second. But we might not be listening to the right thing either. They might have found different ways to communicate. We rely on light. We rely on radio waves, mostly, on other signals, relying on light. They might use other different things. Perhaps also they have seen us and they don't like what they see. Maybe they don't want anything to do with us. And who can blame them, right? If you looked at us and thought, you know what, actually we're just going to stay put over here and perhaps we're going to observe. Perhaps we are just not advanced, right? Perhaps there are civilizations out there who are aware of us, who've seen us develop and think, let's just see what happens first and observe them, right? That's a possibility. But it doesn't mean they are not there, right? The silence does not mean they are not there. There's so many other possibilities, even if they're not observing us. And I want to emphasize that I don't think that's true. I'm not one of these tinfoil hat kind of people. But the thing that we want to remember is the Milky Way galaxy is 10 billion years old. Many, many stars have existed. But for life to exist on Earth, it's taken 4.5 billion years, right? To get to the point where we are just now able to look out there and communicate. So it's unlikely, perhaps, that there are many more that are able to do that. Maybe they only existed for a short amount of time. There's a sad, dark idea, perhaps, that they don't exist for very long. This idea that a civilization's natural lifetime is inhibited by its own willful demise, right? Like that we are demonstrating that perhaps we are not quite capable of sustaining ourselves for much longer. Maybe that's happened many, many times before they were able to do that kind of thing. Sad. But they might not be our neighbours. And I want to keep coming back to this point because the universe is such a vast place that even if we're not seeing them in our own Milky Way, even if they're not coming and saying hi, there's just so many galaxies out there that it might have happened. The sad thing is, they're just so far away that we will never, ever know. The nearest galaxy to us, the Andromeda Galaxy, is 2 million light years away, right? That's still ridiculous. The light takes 2 million years to get from that galaxy to us. So much stuff has happened in that last 2 million years. If we send a signal to the Milky Way Galaxy in 2 million years, the Andromeda Galaxy in 2 million years will be long gone, right? So there's not much point in doing that kind of thing. There's one thing that we have done, which will probably outlive us. And if there is civilizations out there in the long distance future, they will probably meet our robots first. One thing that kind of makes me laugh is our first act in sending robots out into space was to send nudes. We sent them a picture of us naked so they can just, we'll give them a wide berth as well. But like these robots are out there, and if we never meet these aliens, then perhaps they will meet our robots, or perhaps the same will happen to us. Perhaps our first interaction might be with robots going out there, because why would anyone want to travel these vast distances that will probably cause pain and cause the human body a lot of anguish? You're all doctors, you all know how radiation affects the human body. Space is not a nice place. And sending people out into space is not good for the human body either, and they will interact with an awful lot of things. So maybe it's sensible to send robots instead. So maybe that'll be the first thing we see. But it doesn't have to be bleak. It doesn't have to be so sad, because the whole point of today, the whole point of this session was to kind of emphasize that even if we are alone, there is something fairly special, right, and beautiful about the fact that we even exist at all, right? We are living in a universe that has just the right physics to balance atoms being born at the Big Bang, hydrogen and helium, that can then go on and form stars, that can then, throughout their lives and deaths, give us just the right amounts of different materials in successive generations to go on and form planets around other stars. And one of those planets has just the right parameters to allow life to form and cause untold problems for the rest of the planet when we come along. But we are very, very fortunate. And for that, I think rather than thinking about what else is out there, maybe we should think about how grateful we are to exist and how lucky you all are to be stood in this room with me, listening to me talk. Or maybe vice versa. The opposite of this is perhaps how lucky we are to exist, and what are you doing sitting in this room listening to me when we've got such a fleeting amount of time on this planet. But I'll leave it there, and thank you so much for listening. Cheers.
Thank you so much, Tom.
No problem.
So we can put the lights up at the back there. It will really help us feel it's not night time. Well, that talk really didn't disappoint, did it? It took us really through the whole universe again. And it's a solitary lesson to think that if life is out there, it's listening to us. It's got the main images and what it's basing its decision whether to contact us or not are, Love Island, nudists, and Donald Trump. So those bits are maybe not a direct incentive for life to approach us directly, however close like yours. I want to take a few questions before we finish that. I'm sure Tom can answer more questions later on, because he's very good at doing that. As you've seen, he's such an excellent communicator. So yes, first question, yeah.
You mentioned gamma rays being given off by the sun
Mm-hmm.
to the extent of 4 billion pounds or whatever it was, but obviously photons and other rays are given off as well. How are they produced, and what influence do they have on light?
So they are the same. So
Repeats the question for the Zoom people. Is that all right?
so the question was, when I was talking about nuclear fusion in the core of a star, when the hydrogen is fusing into helium, 4 billion tons of that mass is turned into energy, as per E equals mc squared. And the energy is given off as gamma rays. All the light from the sun that we get on a sunny day is that same light. An interesting thing is when that light, those photons, those gamma ray photons, come out of the core of the star, they don't just whoosh through the star. They go on what's called a random warp. The structure of the star is so dense near the core. The core of a star is about 15 times denser than iron is on the surface of the Earth, right? We picture the sun, a star, as being a plasma, which it is. And the stuff that happens in the core of a star is pretty incredible, but it's very, very dense. And even when you transition from that core to the levels just above it, it's still very dense. So those photons immediately butt up against the material above it. So rather than going straight through, they ping off all the protons that are there. And each interaction means some of the energy from those gamma rays then goes into those interactions. And over the course of, could be 100,000 years, those photons going from the core of the star to the surface of the star become short enough wavelength, low enough energy, that when they escape from the surface of the star, they're the lovely sunlight that we appreciate. So even though it takes 8 minutes for the light to get from the surface of the sun to us, because of all that pinging around, it can take tens of thousands of years to get from the core to the surface, and it loses energy in that process.
Fascinating. Thank you. Yes.
Wouldn't they view out of the Earth as a massifying core? I believe it was possibly moved.
Yeah.
That creates a very powerful which protected the Earth from solar radiation, therefore possibly benefited the life on the Earth. What do you think of that idea?
Yeah, definitely. So one of the things, so the question was, aside from the moon and other things that have protected us, the magnetic field, which is born from the iron core, gives rise to an amazing magnetic field, which is something, you are completely right. I missed off that slide, but the magnetic field is one of those things that channels a lot of these high energy rays that come from the sun. And there are still a few high energy rays that come from the sun, like the aurora, for example, these high energy particles. If we didn't have our magnetic field and have it channeling those things down into our magnetic field lines, then Earth would get scorched. Mars is a good example. It doesn't have much of a magnetic field, if any, and it's lost its atmosphere because of it. It got scorched away because of high energy rays from the sun over billions of years. So yes, you are correct. Earth has been protected by several things. The magnetic field is definitely one of them. The moon is one of them. We also think perhaps Jupiter as well, because it's so big. A lot of things that might have been aiming for us might have been absorbed either by the moon, the backside of the moon. If you ever look at pictures of the far side of the moon, is much more popped than the side that we see. So the moon's protected us from a lot of cataclysms, perhaps. So we've got a list of things that makes Earth just that little bit more fortunate.
Thank you. Any other questions there? Yes.
In that case, why don't you have a factor for the magnetism of the moon? Oh, sorry, the magnetism of the Earth core in the
Drake equation.
The Drake equation.
Yeah, so the Drake equation has a number of factors. I think within that, so the question was, why aren't there accommodations for these additional protective properties that Earth has from things like the magnetic field and the moon in the Drake equation? The Drake equation, I can't answer for Frank Drake, but I think it factors some of that stuff in, right? So when it says a planet that is conceived to be habitable. So I alluded to it briefly when I said in the habitable zone, which is this kind of Goldilocks area around a star where water is okay to exist. But within that factor, within that parameter, perhaps you could say, okay, not only does it have that as well, which is maybe why you would want to reduce that factor, that particular parameter in the Drake equation. You could reduce that from a higher number to a lower number, saying maybe not many of these planets have a moon like our moon, or have a magnetic field like our field. But you could add that in, definitely, into that parameter, but I don't know why that's not in there.
Yeah, isn't there a famous quotation that either we're alone in the universe or the life is teeming in the universe? Both possibilities are incredible.
Yeah.
That's a quotation from somebody, I can't remember who it is. It's Carl Sagan, though.
It could be. Carl Sagan was correct for this.
So I think he was-
It's scary. Either one's a scary prospect, right? If we are alone, if it is just us, I think this is a Bill Bryson quote. If it is just us, imagine what that suggests, right? What would that mean? But if it is teeming with life, then again, where are they? And why are they avoiding us, right? But yeah, there's another theory which I didn't include in the slides because it seems a little bit too queasy and bleak. But it's a simulation theory. So rather than a zoo theory where they exist in observers, actually the reason why we don't exist in a universe where we see any life is because we're the only ones programmed into it. And actually we are in some sort of simulation, and there's no interest in running simulations of additional planets with life. So we're the only ones that they're interested in. Makes me feel a bit sick.
It's not like now, is it?
Yeah, this is getting far. So this was meant to be a science talk, so let's not talk about that. But like, if you want to question why there's no one there, then perhaps.
Paul and Barry now to come forwards and give an eloquent thank you to you for this wonderful talk.
I don't know about eloquent, but I know what we want to mess up. So, Thomas, thank you very much for that fascinating journey through the cosmos. I mean, we have learned that time infinitesimally goes in both directions, and space goes infinitesimally, probably through these billions of galaxies. So what are we to take as a group of healthcare professionals or a group of humans this evening into York? What have we learned? So I've scribbled down a few things. We've learned that there's a lot of galaxies. We've learned that we're an afterthought of the stars. I think that's a quote from Thomas. We've learned that Coleridge was right when he said water, water everywhere. We've learned our galaxy neighbours will probably never get to hear Dua Lipa because they're just too far away. And we've also found out why gold is so expensive. I did reach for my scientific physics textbook before I came out just to see if there were any links between healthcare and cosmology. And I picked up The Hitchhiker's Guide to the Galaxy, and I read this section, which I quote: "A wormhole had just appeared in the galaxy. It was exactly a nothing of a second long, a nothing of an inch wide, and quite a lot of a millionth of light years from end to end, as you described. 239,000 lightly fried eggs fell out of it, materializing in a large wobbly heap on the famine-struck planet of Pogril. The whole of Pogril tribe had died from a famine, except for one last person who died of cholesterol poisoning." So, perhaps most importantly, you've reminded us of perspective when we come across patients who are anxious, perhaps because of their cholesterol levels, and we might gently consider that we're made of stardust at that point, forged in the heart of supernovae, because most of our bodies come from supernovae, apparently. And though that perhaps won't be the prompt that those patients need to take their statins, we have learned that astroseismologists use pulsations of stars, kind of a bit like we use ultrasound to find out what's going on underneath, which I also found fascinating. But in all seriousness, you've shown us that rigor and curiosity drives you to understand, and perhaps us, the cosmos, and that also encourages us to understand and heal the human body. So we have plenty in common. So thank you for expanding our horizons, both literally and reminding us that whether we're studying the infinitesimally large or the tiny details in a human body, we're all just trying to make sense of this extraordinary reality that we inhabit. So please, can you join me in thanking Thomas for an excellent talk?